Welcome back to Chapter 9. Let's talk about the Bohr model. So it had been known for a while before Bohr came along and started investigating that if you put a single gas, so like neon or hydrogen or helium or any gas like that, if you put a gas into a tube and you put a high voltage from one side of the tube to the other. So you put a really high voltage on the tube. That the gas inside the tube lights up. It gives off light. Neon gives off a reddish light. Mercury gives off this bluish color light. Helium is kind of this peachy color. These different gases give off different colors of light. So this was known to occur for a while, but people didn't really know why for a long time. And so when people were investigating this, what they did was they split the light up into its individual wavelengths. So they looked at the spectra, that's what we would call it, for these lights. Now a white light source would just give off all of the colors of the rainbow, which would then just look white to our eyes. But hydrogen, for example, that looks kind of orangish, kind of peach in a way. That, when you split its light up into its individual wavelengths, it doesn't give off all the colors of the rainbow. Instead, it gives off very specific colors. So it gives off purple, a blue, and a kind of greenish blue, and a red color. There are very specific wavelengths of light that are emitted from the hydrogen source. And when you do the same thing with helium, once again, you don't see a rainbow of colors. You see very specific wavelengths of light that are given off, and it is always those same wavelengths of light if the gas is helium. From one sample of helium to a different sample of helium, it doesn't change. It's always the same. Going from a different gas to that would change the spectrum, though. So neon was a lot more complicated. So when they put neon in and they look at its spectra, you're seeing many more colors, but it is still only specific wavelengths. It's not a spectrum like the white light source, where it's giving off all the different colors. It is still only giving off very specific wavelengths of light. So, what is the significance of these elements only giving off very specific wavelengths of light? Well, the significance is quantization. There's only very specific wavelengths of light being given off. And since the light is being given off by electrons, because that's what's being excited, if we go back here and look at these lamps, these neon lamps, what's happening is because we're exciting the molecules, the electrons are jumping up to a high energy, and then when they drop back down again, they're giving off light to do that. So the energy levels that these electrons can exist at are quantized. They are very limited. They can only exist at very certain energy levels. And that was where Bohr got his model for the atom. So Bohr suggested that the electrons must exist in orbitals that have very specific energies, and that the electrons can exist in and jump between only these certain energy levels. So these energy levels in hydrogen, for example, were numbered as 1, 2, 3, 4, and 5. Those are the first 5. There's more than that, but we're not going to worry about the higher ones. So the electrons can exist in any of these energy levels, but they cannot exist in between. So you could have an electron in the first energy level, you could have an electron in the second one, or the third one, or the fourth one, and they can move in between them, but they don't like just slide from one to the other. If they just dropped from one to the other through space, then they could give off a spectrum of light. So just be continuously bleeding off energy as it drops from 2 down to 1, or from 4 down to 2, whatever the move is that the electron is making, going from one orbital, well, kind of giving away the next part here. He calls them orbitals, these energy levels. Bohr called them orbitals. So going from one orbital to another, it doesn't kind of just drop from one to another and give off energy as it moves. Instead, the electron exists in the fourth energy level and then instantaneously exists in the second energy level. It doesn't actually move in the way that we think of things moving from one to the other. And so in that instant where it drops from 4 to 2, again, without actually physically just shifting down, it's just in one place and then it exists in the other place. In that instant, the electron gives off light that corresponds with the energy difference between these two levels, because the fourth energy level is higher in energy. The second energy level is lower in energy, and so when it drops from one to the other, that extra energy needs to go somewhere. The electron can't hold the energy and save it or anything like that. The location of the electron is quite literally the energy of the electron. The energy and the location are inextricably linked. And so when it moves from one to the other, that extra energy has to go somewhere, and it is given off as light, which in the case of hydrogen, going from the fourth energy level down to the second energy level, the light that's given off is a bluish-green color. The energy of this photon of light exactly corresponds to the energy difference between these two levels. Going from 5 to 2 corresponds to this violet color, and going from 3 to 2 corresponds with the red color. So the reason that we saw only very specific wavelengths being produced here is because the electrons could only have very specific energies. They couldn't have any energies in between those. It was one or the other, nothing in between. All right. So with hydrogen, Bohr's model worked perfectly. It modeled hydrogen to a T. Everything worked exactly the way that it should. But things got a little bit more complicated when you went to anything larger than hydrogen. So hydrogen has only a single electron. It has a single electron and usually just the one proton. You will sometimes have deuterium, which has a neutron as well, but mostly it's just a single electron and a single proton. That is quite literally the simplest case possible, and so Bohr's model worked perfectly with that. But as soon as you add in a second electron, even if you keep the protons the same, even if you have H minus, as soon as you add in a second electron, Bohr's model no longer works. Now, it's not completely a failure. It's not like it's, you were expecting an answer of 2 and Bohr's model gives you an answer of 500. Like, it's not way outside, it's not completely incorrect, but it is not perfect like it was with hydrogen. It has some pretty big issues when you start adding in multiple electrons. So, despite these shortcomings, Bohr model is still really important, mainly because it really helps us understand quantization and the basic idea of how electrons work, where electrons exist, how they exist in an atom. But to really get into the most accurate way that we have right now of describing electrons in an atom, we need to move to the quantum mechanical model. This is the best theory that we have currently, but even the quantum mechanical theory has its issues. Quantum mechanics is not perfect. It is really good. I'm not beating up on it by any means. It is really, really good at predicting the universe, but it still has issues. Everything in science has issues. We just like to sometimes pretend like we have everything figured out, but scientists actually, we have not figured everything out. But that being said, quantum mechanics works much better than anything we've ever done before, and it works well enough to do really everything except look at the subatomic particles. That's really where things start to get a little bit wonky, is when we're looking at subatomic particles. Anything larger than subatomic particles, quantum mechanics works very, very well. Although most of the time it's not needed for really big stuff. Sorry, I'm starting to get into the weeds here, and I told you we weren't going to do that. So just very briefly here, describing what quantum mechanics does. In the Bohr model, and in really everything we do in life, we think of things as discrete objects, as particles that move around. That's the way we think of things. But when it comes to electrons, and other things that are on the order of size of electrons, we don't really want to think of them as particles for most of the time. Instead, we're going to think of them, instead of existing as a particle that moves in a very set pathway, we're going to think of them as existing in a probability field. So instead of saying the electron is right here, there's the electron. With quantum mechanics, we say, well, in this region, we have a 70% chance of finding the electron. And so you could even draw a larger circle here and say, there's a 90% or 99% chance maybe in this larger region that the electron exists in here. So we think of things in terms of probability instead of thinking of them in terms of particles flying through a known trajectory. So in baseball, you throw the ball and it moves along a very defined path determined by the friction of the air, the friction of the fingers of the pitcher that threw it, the amount of force put into the ball. There's all these factors that go into play into determining what the trajectory of the baseball is. That's the classical mechanics. But in quantum mechanics, we say, no, it's not just a particle with forces on it that we can predict what's happening. Instead, these particles exist as a probability field. So we can still define a region that would look very much like this trajectory, where we are very likely to find the baseball, but it is not a discrete particle like that, where we can track it as it moves along. Alright, I hope that's clear as mud, maybe a little clearer than mud. In the next video, we are going to talk about how we determine, using the quantum mechanical model, where electrons exist in an atom. And we're going to use an analogy to try and make it a little bit more clear, because it can be a bit confusing as to what we're talking about. But we're going to treat our electrons like they are packages in a warehouse. And our quantum mechanical model is going to be our packing system in the warehouse that tells us where our electron packages need to go. So we will talk about that in the next video.